Hello. What I want to do is finish up chapter 40. I should actually be able to finish the whole thing, give you a broad overview of mostly population growth and demographics. And it'll give you a good insight into what ecologists study, although it's not everything. We would have had two more chapters where we talked about symbiotic relationships and conservation efforts and stuff like that. But this is at least a really good introduction. So yesterday I talked about how dispersion and population size is something of interest to ecologists. Determining population size can be done three different ways, and the best way was that mark recapture method that I talked about yesterday, and I gave the example of the roaches and putting fingernail polish on their back. Ecologists are also going to look at patterns of dispersal, clumped, uniform, and random. And so one of the reasons why they would maybe want to do this is if there was going to be a construction or a building being built. You want to look at the patterns of dispersal of different organisms so that they're not disrupted too much. And there's other reasons, but that's the one that I can think of off of the top of my head. Demographics is what we're going to talk about a lot today, which is the study of the statistics that affect population size. And additions are going to occur through birth, and subtractions are going to occur through death. That's the first thing that's going to be looked at is birth minus death over a certain population size is going to give you either a growth or a decline rate. What you can also do with that information is construct a life table. So if we look at this table right here, this table is the life table for ground squirrels. And so one thing I want you to notice is that it's divided into females and males, and then it's further divided into age, living, deaths, and then finally death rate. And so what you want to look at, the most important thing to look at on this life table is the death rate. The death rate over the lifespan of the squirrel population. And what you will notice about squirrels is that the death rate actually stays pretty consistent over time. The other thing you will notice is that females tend to have a longer lifespan than males, which makes sense because males are more, out there putting themselves in danger. What you then do with a life table is you can construct a survivorship curve or assign a survivorship curve to that animal. And so you'll notice here we have a type 1 survivorship where humans would fall in, low death rate at a young age, higher death rate at the end of the lifespan. Type 2 is that a constant death rate over the lifespan, and so the squirrel we just looked at would fall under that category. Type 3 is a high death rate early in life. So high death rate early in life, so things like oysters. The other thing I'd like for you to know from this chart is humans, because there's a low death rate in early life, are going to have fewer offspring, and they're going to be larger offspring. The animals that fit under a type 3 survivorship are going to have a lot of offspring. And that makes sense. If there's not a strong survival of offspring, you want to have a lot to increase the chances that some of them are going to carry on the genetics for that population. So question, each female fish produces millions of eggs per year. Draw and label a survivorship curve for fish. So basically all I'm really wanting to know is where do fish fall in? Type 1, type 2, or type 3? Since they're having millions or they're laying millions of eggs, that should give you a pretty good indication that they belong in survivorship curve 3 because there is going to be a lower survivorship of the young. So they need to have more young. All right, so that's survivorship. Changes in population size, like I said before, is going to take into consideration births minus deaths. Immigration and immigration are not going to, or they're considered equal. They are not being taken into consideration when we talk about changes in population size. So while this picture isn't complete, it's what we are going to look at today. So immigration and immigration are not taken into consideration. dn over dt is a change in this population size. So how many extra individuals are being added over a certain time period, or how many extra individuals are being depleted, I guess. for lack of a better way of saying it, over a certain time period. So dn over dt. N means population size, the original population size that you start with. T is the time period, and then you take births and you subtract deaths. So births minus deaths pretty much going to give you how many individuals were added over that time period. And so this brings up a pretty interesting topic for demographers, is population growth of humans. And so you can construct a table like this that will tell you, does the birth rate equal the death rate? Does birth rate exceed death rate, or are they equal? And so when there's zero population growth, that means that the number of births is equal to the number of deaths. And so countries or places where we're going to see this would be Russia, Germany, Japan, Poland, Austria, and Italy. So we're going to see them oscillate between 0 and negative. So what are the consequences of that? Well, zero growth rate can actually help a country by raising wages and reducing government spending on the needy. The problem arises when these places are going to move into the negative growth rate. That can actually have a pretty negative effect on the economy if you're not replacing your humans that are dying. Okay, and so we can assign two different types of growth to populations. The first one is exponential growth, and the second one is logistic growth. And so for exponential growth, you can see that it's a J-shaped curve, and for logistic growth, it is shaped like an S. And so we'll talk about each one of these and what they each mean. All right, so an exponential population growth means that it is just, there's not a capacity that's being reached, and the reason why a capacity isn't being reached is because they're in ideal conditions, and the population is going to grow really rapidly, and the resources are considered unlimited. So a capacity is not being reached, nor is it known at that time. So when animals like these African elephants are put on reserves or on these little sanctuary sites, you see exponential growth. And usually that is the purpose of putting them on these reserves, is so they can have unlimited resources because they were endangered to begin with. The way that you're going to do calculations for exponential growth is using this formula right here. So the change in the population size, as indicated by dn over dt, all that means, it looks kind of scary, but all it means is how many extra individuals are being added. That's all that means. And what you do is you take R, which is a growth rate, and you multiply it by N, which is the original population size, and that will tell you how many extra individuals are being added. So here's a sample problem. So a certain population of mice is growing exponentially. So if it says that, then you know to use this formula right here. The growth rate, R, is 1.3, and the current population size, N, is 2,500. How many mice are added to the population each year? So in the first year, all you do is take 2,500, multiply it by 1.3. Looks like there's 3,250 that are being added in the first year. All right? And so what you would do to get the total population size is then add that to the original 2,500. All right, so just to kind of re-say what I just said, if it's exponential, you're going to use this formula. Plug in for R, plug in for N, and you get 3,250. That means 3,250 mice are being added in that first year. All right, and I apologize for giving you a really old statistic. I'm sure it's gone up since 2009, but either way, this is the word problem. In 2009, the United States had a population of about 307 million. So in that year, we were considered to still be at exponential growth. So we would use the exponential growth formula. If there are 14 births and 8 deaths per 1,000. So what you can do with these numbers right here is you can actually calculate a growth rate, because what you'll notice in this word problem, R is not given. N is given, but R is not given. So you would have to calculate that, which is pretty simple. So I want to know, what is the rate? What is the blank per blank? Well, if there's 14 births and 8 deaths per 1,000 people, well, how much growth per 1,000 people? It would just be 14 minus 8. All right, so we would do 14 minus 8 and divide that by 1,000, and you would end up with 0.006 as your R. And then you would take 0.006, you would multiply it by 307 million to get 1,842,000 extra people added that year. So exponential growth, like I said, it is believed that humans maybe are still at exponential growth right now. It's kind of hard to tell. On the reserves and in the sanctuaries, it's definitely something that is happening with those animals, but unlimited resources are rare and it's just unrealistic to have exponential growth. The more realistic growth model would be the logistic model, and what it's going to take into consideration is what's called carrying capacity. Carrying capacity basically is at what point can the environment no longer sustain any more growth? At what point are they going to max out on resources so that the population cannot get any bigger? All right, so K is the letter that is going to be used for carrying capacity. The shape of the graph, it's an S. And the formula is this. So you still have dn over dt, which just means how many extra individuals are being added, or how many individuals are being subtracted overall that year. You still have your R, which is still the growth rate. Still have N, which is the original population size. Now what you're going to do is just incorporate that known carrying capacity into the formula. And so if you get a word problem, you would just plug in to this formula right here. And here's your sample problem. So if a population has a carrying capacity of 900 and a growth rate of 1.1, and the original population was 425, what is the growth? How many more individuals are being added that year? So we're just going to assume that the growth rate is per year for this one. So you plug 900 in for K, you plug 425 in for N, you plug 1.1 in for R. And if you want to pause the video right now so that you can calculate it, go ahead and pause. All right, so what you would have gotten when you calculated it was somewhere, probably you would have gotten 246.7. I would just round that up to 247 individuals added that year. Because as carrying capacity is approached, growth rate is going to slow. So that's why this formula is being used. All right, I want to talk a little bit about life history. So we're going to skip to life history and the study of the reproductive patterns of different organisms. Okay, I am on. I'm just making sure I'm not going too fast on the notes. So life history is the traits that affect an organism's schedule of reproduction and survival. There's 3 variables that are going to determine life history: the age of sexual maturation, how often an organism reproduces, and the number of offspring during each event. So that is going to determine the life history. And then note that these traits are evolutionary outcomes. They're not conscious decisions by the organisms. So natural selection has shaped these organisms, or shaped these different species to have a particular life history that's conducive for the survival of that organism. So here's an example: rabbits. So the average rabbit is going to reach sexual maturity at 3 to 8 months old, and they're going to reproduce for the rest of their 9 to 12 plus years. Once a rabbit has a litter of babies, she can reproduce starting the next day, which is super crazy. Okay, so what else is also really interesting is they don't have like an estrus cycle. They are more or less ready to mate all the time. There's no menstrual cycle either, and there's no window during which pregnancy can happen. So we know with humans, a typical female is going to have a 28-day cycle, where day 1 is the first day of her menstrual period, and day 13 or 14 is when she ovulates. And then somewhere around day 20, yeah, when she ovulates around day 13 or 14, sorry, and then she's able to get pregnant during that kind of middle window, no matter what. So there's nothing that a man can do to induce her to ovulate. He basically has to catch her at just the right time, pretty much. With rabbits, it's different because when they have intercourse, that induces her to ovulate, and it can happen at any time, which is pretty cool. So after 40 seconds, the egg is emitted for fertilization, and she is going to be pregnant with usually between 4 to 12 babies. And she will gestate, meaning she'll be pregnant for only 30 days. She, like I said a minute ago, when she has her litter, she is ready to get pregnant again the next day. And she's looking at about 100 babies per season and about 1,000 babies per rabbit per lifetime. So pretty crazy reproductive pattern in rabbits. Some other vocabulary words, simulparity and iteroparity. I want to make sure I distinguish between the two of those. So simulparity means big bang reproduction with many offspring at one time and that the individual dies afterwards. This is going to happen in less stable environments. The individual doesn't always die afterwards. What I'd like for you to write down for simulparity is this is going to be that type 3 survivorship. Type 3 survivorship. It's in a pretty harsh, less stable environment, kind of like where the oyster lives. And the adult is going to have many, many offspring. And because of the energy that it takes to have that many offspring, they will likely die. But it's worth the sacrifice because that amount of energy is going to maximize the amount of offspring produced. And remember, with type 3 survivorship, there's a low survival of offspring, so it maximizes the potential for some of those offspring to survive and carry on the genetics of that particular strain. So the agave plant's going to do that, which is pretty interesting. Iteroparity is going to match either type 1 or type 2 survivorship. That means there's repeated reproduction, few but large offspring, and it happens in a more stable environment. So the offspring are more likely to survive, or like with the squirrels, there's a constant death rate over time. So it doesn't really matter if they're old or young. So iteroparity is going to be kind of what humans are going to fall under and what most mammals and reptiles are going to fall under. All right, another way to look at reproductive patterns and to kind of match it up to those survivorship is K selection and R selection. So how is natural selection molded these species to reproduce the way they are? So K selection is going to match type 1 and type 2 survivorship. It's going to match iteroparity. So the organism maybe lives around carrying capacity or is approaching carrying capacity. There's high prenatal care, so the young are more likely to survive. There's low birth numbers, good survival of young, and it's density dependent. So what that means, density dependent, it's kind of like if you decide you want to have babies, you have 2 kids, you decide this is enough, and you stop having them. That is a density dependent type of reproduction. So remember, K selection is going to be living around. Natural selection is selected for these organisms to have few births, take care of their young, and to stop breeding whenever they have enough babies. R selection is going to most likely match that type 3 survivorship because there is going to be an exponential growth depending on which organism you're talking about. But for R selection, natural selection has selected for these particular organisms to have a high birth number with little or no care. There's poor survival of young. That's why this is type 3 survivorship. And it's density independent, meaning a fish doesn't all of a sudden decide like, I've had enough babies, I think I'm going to stop. Or a cockroach doesn't say, I think I've had enough. They just keep breeding like out of control. So this is another way to kind of match it up. So what I would say is type 1 survivorship is K selection, and the method is called iteroparity. R selection is going to match potentially simulparity. that we talked about before with the agave plant, and it's going to match that type 3 survivorship. So this kind of helps you organize it in your brain and categorize it a little bit better. All right, things that can limit a population growth, an existing population, things that can limit an existing population growth are density dependent factors. Density dependent meaning the size of the original population matters. All right, so examples of factors that will affect a population and are density dependent are predation. The more individuals there are, the more likely a predator is going to see them. Or you could think of it as the less individuals there are in a population, the more likely the population can be devastated by predation. So it depends on which angle you're looking at it. Disease, kind of like what we're doing right now. The spread of a virus is definitely density dependent and can have an effect on a population size. So the larger the group of individuals, the more likely disease can spread, the more devastating effect it can have on that population, which is why quarantining, why we're doing this right now, is that we reduce the density so that the disease is less likely to spread and have an effect on the population. So very good connection there. Competition, the more individuals there are in a population, the more competitive they're going to be for resources. Territoriality, the more individuals there are, the more territorial they'll become. And then waste accumulation and physiological factors. So those all depend on the size of the population to begin with and can have an effect on the growth of that population. Density independent factors, things that can reduce a population size without any regard to how big that population was to begin with, are natural disasters. And that's probably pretty obvious. All right. What you see here is called a boom and bust cycle. And this is a predator-prey relationship. So biotic and abiotic factors are going to have an effect on populations, and population sizes are always going to fluctuate based on biotic and abiotic factors. Weather would be an abiotic factor, and predator-prey relationships would be your biotic factors. So if you see here in this chart, you have wolves and moose, and you have harsh winter. So the harsh winter weather is going to have an effect on the moose population, and if the moose population goes down, then the wolf population is going to go down, and they're interrelated here. When one goes down, the other one follows. When one goes up, the other one follows. And so just kind of a neat way to look at the relationship between two population sizes. So here's an example of two other populations that we can compare, and you can kind of see a trend between them. This is a predator-prey, another predator-prey relationship. As the lynx population goes up, they're going to prey on more hares. The hare population would potentially go down, and vice versa. If the hare population goes down, the lynx population would go down because that's their source of food. So that's called a boom and bust cycle, predator-prey interactions. And there, it just shows that the two population sizes are interrelated based on the predator-prey relationship. All right, we are almost done here. Just kind of a last thing about human population growth. You have two types. You have type A and type B population growth. Type A is high birth, high death. Type B is low birth, low death. Usually your less educated, less advanced places are going to be type A. Your more educated, more advanced places are going to be type B. And as a place transitions from type A to type B, that's called a demographic transition. All right, and these age structure diagrams is how we're going to make a visual of the demographic structures. Right here is an age structure diagram of Afghanistan, United States, and then Italy. And so what you can see with Afghanistan is it is that type A, high birth, high death. The United States has a little bit of a slower growth, a little bit higher birth than there is death. And then, as we talked about earlier, that no growth Italy has zero growth. This is probably the best place to be because this means that the country is more advanced, but we don't have as much of a threat to go into a negative growth like Italy could, which could cause their economy to suffer. All right, and then lastly, the last thing I want to touch on is global carrying capacity. I apologize. This is a 2015 statistic right here. Let me get you the actual one. The actual current world population that I am seeing here on my internet search is 7.8 billion. So we would just put a little loop here and a little loop here to make that 7.8 billion right now. Like I said before, some believe we are at an exponential growth with unlimited resources, and we all most of us live our lives as if there are unlimited resources. But it's starting to become a concern as the projected carrying capacity of anywhere between 10 and 15 billion. So this number is what is believed to be the projected carrying capacity. And there's a question mark right here because the way that we are using resources is going to have an effect on what our carrying capacity ends up being later on. And so what we do is we can look at what our ecological footprint is. And so each person or each population or each country has their own ecological footprint, which means what's the total land and water area needed for all the resources a person consumes in a population. And so a person is usually going to use 1.7 hectares, which is 1 hectare would be a 100 by 100 meter plot of land. So it is believed that 1.7 hectare per person is what is sustainable. However, the typical person in the United States is going to have a 10 hectare footprint. And so if that doesn't get reduced, if our ecological footprint or the effect that we have on the environment because of what we use and how we go about our typical day, if that's not improved upon, then this carrying capacity number just keeps going lower. So in class, I would have had a discussion on what can we do, what are the consequences, what are the solutions, and we could have talked about things about, conserving ecosystems, not driving, walking or riding a bike instead of driving, pollution, something simple as don't use a paper plate, use a regular plate and just wash it and reuse it, and so things like that. So hopefully you've gotten a pretty good overview of a certain angle of ecology. Of course, we talked a lot about populations and demographics and whatnot. We would have talked a lot on chapter 41 and 42 just about symbiotic relationships and conservation efforts and how humans are exploiting certain ecosystems and stuff like that. So I hope this gave you a pretty good overview. This does end our ecology unit and basically any new content for the year. I will launch test prep next week. Like I had said before, there will be some interesting new things that you can learn about old topics that we've already covered. All right, so I will see you guys later.